The next speaker is a very interesting person because he's a code dive veteran, and Andrzej Krzemieński has never missed a code dive even once, so it's going to be his 6th time, and that in itself I think deserves a big round of applause. Thank you. Andrzej has been a software developer since 2004. He works mostly with C++ in commercial software, which includes safety-related and high-performance systems. He's a member of the C++ Standards Committee and a Boost developer, and he's also a co-organizer of the C++ user group in Kraków in Poland, and he's known to the community for his blog on C++. Now, the title of his talk, it sounds really impressive, and it's incredibly difficult to pronounce, but let me try. Preconditions, postconditions, invariants, how they help write robust programs. Let's put our hands together for Andrzej Krzemieński.
Thank you. Okay, so hi everyone. I can see you can hear me. Thank you for attending this talk. It will be about, those difficult words, preconditions, invariants, less so about postconditions. And first, they're already there. Consciously or not, we are using them. So the choice here is to be aware of this, of their existence or not. Second, we'll see how they are used by different people today. And last, we'll see what a language can do to help handle them. And before any definitions, we will go through some motivating examples. This is functions that you will often find. It checks whether one of the offers or which of the offers is better, and it gets us the result. And because we see this pointer to reference, sooner or later we have to ask this question: what if one of those pointers happens to be null? And that's it. So for now, we are just asking this question. So here's a second example. We have a function that gets some integer and a range represented by lower and upper bound, and it returns us the answer if this x is in range or not. And there is no pointer dereference here, so it looks like everything is fine. But what if this low is greater than high? What if? And another example. We get a C-style string, and we need to compute its length. So, of course, we need to ask, what if we are given a null pointer, but also, what if it's not null and there is some characters underneath, but if we iterate over it, there is no 0 to be found anywhere? What then? Those are the questions. Let us contemplate about them for a while. And let me show you yet another one. This function looks really simple. It just takes an integer and just gives us the answer whether it's even or odd. It looks almost impossible that anything could go wrong with it. But can you see the catch here? Negative numbers. No, it works for negative numbers. -1 is all ones, so it will still say 1 is odd. -2 is even. It will work. I checked it. There is no catch here. It just works. And more important thing is, those functions really exist and are really neat because we don't have to answer all those questions. And we call them white contract functions, which means any input value is fine. Whatever you give me, I know how to answer how to give you the answer. And in contrast to that, those functions that we've seen before, like length, we call them narrow contract functions, which means some inputs the compiler will eat them like null pointers, but we consider the authors of the functions or the callers of the functions, we consider them invalid. And going back to one of the initial examples, we can see the declaration like this. And there are two parts of the types of the input parameters. We have this offer, which represent the concept, not like C++20 concepts, but the abstract concept that we talk in normal life. We talk about the offers. I can offer you something. You can offer me something back. So it's the part that represents some real abstraction that we want to talk about. And the pointer here is something that doesn't really talk about the abstractions. I needed to use it for some technical reasons because I chose this language. This language uses pointers. There were technical reasons, but they have nothing to do with business logic. And this basically can be told about every type in C++. It consists of two parts. On the one hand, it represents abstractions or concepts that we want to talk about. And on the other, there is some engineering ballast, let's call it like this, something that we have to live with because we are programming in a language. And we can say the same about the entire programs. On the one hand, they represent business logic, and on the other hand, they represent some language-specific ballast that we need to live with because we chose this language. I could have declared my function like this, just taking those offers by value, and I wouldn't have to answer those questions about null pointers. But even the offer alone carries some language-specific ballast. Like the offer may not be copyable, so my function will not even compile in some context. Or maybe it compiles, but if I need to do the copies, it will take so long that the program may be correct, but no one will use it because it's too slow. So even the simple thing as being able to be copied and passing by value carries some language-specific ballast that is not related to our real-life abstractions, because offers in real life are not copyable or not copyable. I could have used a reference and passed these arguments by reference, and this is usually a good thing to do if we can. But references have their own ballast. We'll not dig into this, but they have their own problems. They don't represent constants. They can change over time. The objects underneath constant references can change, even if we often don't think about them this way. But another reason may be that there is some other engineering ballast in the outer context. Like maybe I'm storing these offers in a vector. I cannot store them by value because they are not copyable or too expensive to copy. I cannot store references because vectors cannot store references, so it needs to be a pointer, and I need to sort them. So I will have to use pointers and live with a situation that from the type system perspective, some values are accepted, but they mean nothing in our business model. Like null pointer offer is not an offer. So it cannot be better or worse than any other offer. And the contract expressions like preconditions, what they do is to help us define and talk about these gaps between the business logic and between the type system. And the failure to recognize the difference between the two causes many bugs. So business logic is an offer, in our case, from a real life, and from the type system perspective is pointer to a const object of class offer, and they are different. And usually what we will see in the code is, in the declarations of our function, is a comment, because we have no better means of communicating this difference between the type system and what we are really talking about. So we will have to put it in the comments in order to communicate to our callers. Because there is a potential risk here, because we see the problem inside the function, And we may be led to thinking that we have to do something about it inside the function. But it's actually the caller's problem to understand this difference and to make use of it. So we have to communicate it either in documentation or in the comments so that he or she, the caller, doesn't make those mistakes. And the semantics at the high level is, if you don't respect this constraint that we have put here, our function is meaningless. It may do something, may return something, but it isn't an offer or a better offer. Now it's just a low-level computation on pointers and nothing more. So let's get back to the first question. What happens if one of those pointers is null? Because if we execute the program, something will happen. And the C++ gives us the answer. It is undefined behavior, or UB for short. I will be using UB because it's so commonly used term that it has to have an abbreviation. But this is at language level. What will happen when the code is executed? We don't know what, but most likely it will be one of those two situations. On some platforms, 0 can be treated as an address as any other. So we can go there, maybe it exists, and maybe it has some values, and maybe we can, it's using income. So maybe we can extract some income. There will be some value. It was never meant to be interpreted as income, but maybe it will be there. And we can compare it against other incomes and return value. And if we are a financial server that needs to do serious decisions about trading, and companies' business depends on it, we will be doing these decisions based on random numbers. You can get into serious financial problems, but also into legal problems, because you are doing operations on random numbers. But the other thing that can happen, and this is more likely, is that the program will stop immediately. It will crash. And one thing is important to note here. It will crash because someone put a lot of effort to implement this feature of crashing the program early as soon as something bad is detected. This is done to, the system will do it to protect itself, the system, from your application, to protect other applications from your application if you are accessing memory at random points. And it will also do it to protect yourself and your program from itself in order for it not to do random operations anymore. So it is a very useful feature, and someone had to implement it. But there is one other thing that can happen with UB. It can help detect bugs in your program, and I mean statically, not without even running the program, just by observing the flows in the program, the abstract syntax tree, and checking if there is a situation that will lead to undefined behavior. So let's see how it works. And we heard it this morning, that all the tools, the compilers, code reviewers even, should assume that it is never the programmer's intention to cause undefined behavior. So if we are able to find one in our program, it means there is a bug somewhere. Like, let's imagine that our function is inline, so that the static analyzer can look inside the body of the function to see what's going on, that there are pointers being the reference. And then later on, if there is a call like this that passes a null pointer here, static analyzer can detect that there is a control flow that leads to a null pointer being the reference. And it gives us a warning. It doesn't know what happens. It doesn't understand the logic of our code, but it knows one thing. You never wanted that. So the programmer should go back now and see what is wrong. And of course, no one will be passing null pointers like this. The control flow will be something complicated. There's ifs, there are some exceptions thrown, caught at random places. You may think you covered every path, but the static analyzer can see better, and it can warn you. One good thing about our constraints like this is that usually we can express them as C++ expressions and or C++ functions, like here. It is a valid code. If we put it inside the function body, it would compile. And we can make use of it. As we said, it's a caller's responsibility to understand how we interpret these values and to make sure that bad values are not passed. But if they are passed nonetheless, we can do something to prevent damage and alert the caller that they are doing something wrong. So we can execute the condition as the first thing when we enter to the function and then respond to this. But the thing is that to execute the predicate is easy, but to respond is hard and actually impossible to do in a satisfactory way, because the place of the bugs is the proper way of handling the bugs is to not have them in the code. Once you have them and detect it at runtime, you cannot fix it. You can just mitigate the consequences. So we can just apply some safe default, like return false. We cannot say for sure that this offer is better than this one, so we say it isn't. Just some default. And it may look clever, but it has some problems. First, we have artificially widened the contract. It used to be a narrow contract. Now it's wide, but the other values that we allow, null pointers, make that we are no longer talking about the offers. Now we are talking about the pointers. And this function is just doing some, or we say this function is just doing some operations on the pointers. Maybe you can interpret it as offers, maybe not. We have lowered the abstraction. And the second, it looks like a predicate, but it doesn't fulfill the mathematical properties of a predicate. Like we would expect that if the first equation here holds and the second holds, we would expect and assume that the third one will also hold, but it doesn't, actually, because we didn't pay attention to stick to the mathematical properties of a predicate. Which means that the algorithm, if we use sort, for example, will make this assumption, and if it sorts with this predicate, it is likely that it will never terminate. These assumptions will, because it's making these assumptions, will cause that it will go from one place to another on end. So a different thing we could do is to throw an exception. And this way we guarantee that nothing below is executed also, but also we interrupt our callers. We make a signal that you did something wrong, you need to be canceled. And it may work to some extent, but it works under the assumption that whatever caused the bug, whatever the source of the bug is, will no longer be visible at the place where we catch the exception. But this is not necessarily true. And there is other point here now. Static analyzer can no longer help us, because now there is no undefined behavior inside. If we pass a null pointer here, the static analyzer can see that it leads to throwing an exception, but throwing an exception is nothing incorrect. You throw exceptions in valid programs. So the static analyzer cannot help us there anymore. We compromise static analysis in order to save something at runtime when it is too late. Okay, this gives us different causes for those null pointers being passed. Maybe the reason for a null pointer is a data race in a completely different part of the program. So what that we throw an exception and catch there when the undefined behavior is still there and is still corrupting our program? So a better idea might be to immediately stop the program. The moment we discover that something is not as we wanted, that our caller didn't understand the interface, or there is some other UB going on already, we just stop the program. And this may look harsh and unacceptable, but it has some advantages. We guarantee that no further damage will be made by this program. And as a side effect, we get a core dump that the programmers, if they get their hands on it, can make some analysis on and determine what the problem is. It may look too harsh, but it's option one should consider, even for the systems where the human life depends on. Like imagine troops having a software that helps some tool that helps detect whether there are some enemies in the vicinity. In the night, you cannot see people, but the tool could detect how many people there are in the vicinity. This tool had better work correctly, and this tool had better not crash, because soldiers' life depend on it. But, so there's a lot of tests going on and a lot of effort to make sure that everything works correctly. But if at runtime we were to detect that the program is starting doing unanticipated things, that we may be operating on random values, the only decision we can have is to shut down and say to the soldiers, sorry, you're on your own. And now you will piss them off. You are risking their lives, but you are giving a clear and very important message. Now the tool can no longer help you. You have to use only your experience. Whereas on the other side, if we were to proceed with some default values or some random computations, we are risking lying to the soldiers that depend on us. We're saying, well, we don't know what happened with default. Safe default is 0. There is 0 enemies in the vicinity. That would be even worse. So it's always an option to abort, even in safety-related systems. And so far, we have been talking about a precondition. So maybe let's look closer at it. Precondition is a predicate, that is a function that operates on our arguments and returns true or false, that expresses a constraint on the input values. We say that we expect this condition to hold when the moment the function is executed. And expect is not formal. So the formal way of saying this is, if it is not true when the function is called, it means that there is a bug in the program somewhere before this function call. Not immediately before, maybe a day before this function or a different part of the application, but somewhere before rather than after the function, which means that, or we will talk about this later. So this function will be executed nonetheless, but if this condition doesn't hold, whatever value we produce is meaningless. We are no longer talking about the offers here, but we are just talking about abstract machine and what it does. Also, because we say the bug is before this function call, when we get to fixing it, it is clear on which side of the interface it needs to be fixed. We don't fiddle with the body of the function, it's okay. The callers, one of the callers has a problem inside them, so this is where the fix should be applied. So the way precondition helps detect bugs is that it defines them formally in a way that other programmers, code reviewers, and tools can understand it, because it's expressions from the language. And if we are thinking about standardizing support for those preconditions and contracts and other contracts in the language, we mean providing the uniform syntax that will be uniform for all the tools and applications that there are in the world. And any particular semantics, like whether they are evaluated, what happens then, are secondary. Our goal is to provide a language for talking about those predicates, the preconditions, invariants, postconditions. So let's see the second example. The question was, what happens if we need to check even integers in the range, but the range has the inverted or not inverted? There are some integers that do not represent a range. And what happens then? And one answer is that there is no UB here, no undefined behavior. So maybe there is no problem here. There will be some value produced. You give whatever ints you get, there will be some computation, some comparisons, some value will be produced. If the caller gives us rubbish as input, they will get rubbish as output. It is not our problem. But it's not entirely so, because now we are lowering the abstraction again. It's not ranges anymore. It's just 2 integers and some computations. And also, potentially there will be bugs in the code. Our callers will make mistakes, like, I thought that this value goes at the end because other libraries do it. But in fact, in my library, it's at the beginning. So I may have confused how the order in which the arguments are passed. And we have lost the opportunity to detect this bug in our function. It's not our duty, maybe, but we can help. So we could consider, even though no one asked us about it, and we are protecting against nothing, because from the perspective of the body of this function, we don't have to do it. But maybe we want to check and immediately abort the program to indicate that there is a bug going on. Or maybe we can go even further, and this may look crazy, and just plant UB, even though there was none before. If this condition were false, we just dereference a null pointer, and we cause UB. And this may look irresponsible, but I realize how dangerous UB is and what consequences there are. What I'm saying here is that bugs in the code should be treated equally severely as undefined behavior, because bugs are nothing more than undefined behavior at the level of business logic. In either case, our program does something that we never wanted. But why do we do it? Because static analyzers cannot detect preconditions because they don't know what a precondition is, but they can detect undefined behavior. So with this code, we are going back to the situation. If there is a path in the program that caused to this UB being invoked, the static analyzer has a chance to see it and warn us about it. And other tools like UB sanitizers, which are designed to detect UB, can now detect our preconditions. And of course, this doesn't have to be plain there in the code. We can hide it under a macro, which will expand to UB only if we are doing some analysis or tests, and the normal program, it can do nothing or abort whatever you choose to be the safe default. But luckily, we don't have to do all this stuff, because there is another way, which may be even better. We can introduce a new type, range, which will be 2 integers inside, so nothing more here. But the range, because it groups these arguments, it gives a clear message what we are doing here, that we are actually using some abstraction like range. And now the callers are forced to type this range. And if they get the order of arguments wrong, now we get a type system error. And the compiler, not even the static analyzer, the plain compiler is forced to report this as an error. But we didn't actually answer our question, we just restated it. Because what happens if this dot low, because now we have member functions, public, const. What if this low is greater than high? And this is answered inside the class definition. Our class will probably look like this. We have a constructor, we have these accessors, and apart from that, we are providing an invariant. And this is nothing that the language can recognize, so it has to stay in the comment. But this is a very important information in this class, and in fact, the only reason for providing this class. We are saying that the two integers that we hold are not just random integers, because if they were, we could use stud tuple or stud pair for integers. This class is different because apart from those integers, it has the invariant, even if we have to communicate it informally. And the guarantee we give is that you will never observe this low being greater than high. So you will also always observe that it's less than or equal to high. And in order to guarantee that, we cannot expose those members as public, because then anyone could compromise our guarantee. So they will be private, and we will only get them through a narrower and safer interface. But because it's an expression, the expression itself is expressible in C++, we can declare it as a member function. It will be const, it will return true or false, and whoever wants can invoke it to check whether we are actually providing this guarantee. And in fact, even we ourselves can invoke it whenever a public function is called. We can check, at least in test builds, but maybe also in production builds, whether the invariant holds. And we could use this invariant when expressing the precondition of our function is in range, but it's not necessary because this invariant, this precondition is implied on any function that uses our type. This is actually the definition of an invariant. Whoever uses this function will get this as a precondition. It's precondition guaranteed to everyone around. So we don't even write it down. It's enough that we put it as an invariant. But how can we provide this guarantee if someone can deliberately pass the high and low the other way around? And for sure, we'll later observe this, not the way we want it. So we have to go back to the definition of the class. It will also have a precondition on the constructor. Like this L cannot ever be greater than high when you call this constructor. And only then can we guarantee our invariant. So the invariant is a conditional guarantee. And this is why this is called contracts, because there's two parts involved and we expect something of both of them. I will guarantee you that this invariant always holds when you observe my type, provided that you guarantee that when you call a constructor or maybe some other function that mutates the values, that you will pass me the correct values in. And this may seem like a little because this bug is still there, but other bugs, like this one, are already fixed. Like this will never happen again, this wrong order of arguments, because now we have a type that binds the two together. We have also fixed another bug. If we manage to propagate this new type range across different layers of the application, the only place where bad values can enter is during the construction. But later on, when all the other parts of the program speak in terms of the range, there is no way anything go wrong. So we have narrowed the scope in the program where the bad values can enter into the system. Like if some functions return just to integers and the function bounds never thought about this being less than the other one because at the level of bounds they are just two numbers, this could happen. But if bounds can talk in terms of range, the only misunderstanding can be inside function bounds, but not outside. Yeah. So now let's get to the third example we've seen. We are computing the length of a C-style string. We know it cannot be null, and we know it must be null terminated. The first thing, the first precondition is easy to express. The second one is in fact not expressible at all. In order to check this, we would have to iterate over all the characters, but if there is no zero there, we will iterate forever and cause some undefined behavior. So there is no way to runtime check it. But there are other options, like we can introduce a new type like C-string, which actually contains this construct star inside and nothing more. So it's the same size, but the name of the class, only the fact that the class exists, sends us a clear message that we don't mean any construct star. We only mean those that represent C strings. So the class definition will again have an invariant, which we cannot express. And observe this. This is interesting, at least. The only purpose of this class is to have the invariant, and we cannot express the invariant, and it is still worth it, because invariant is something we communicate human to human. So we know what we mean, even if we cannot actually execute the code that will check it. And this already handles some bugs. Like if there is function getName that already returns this C string, and my function length expects a C string, there is a type match, and everything is safe. And we know there is no unintentional bug in there. But there will be always some APIs that will use naked construct stars, so we have to prepare for them. Our class will also have a precondition that the pointer needs to be correct. And again, we cannot express the precondition because we don't know how. So as we said, there is no way to check it at runtime, but static analyzer can still help us there. So there is value in trying to somehow annotate formally that we have this expectation. And this is how we could do it. I mean, we cannot do it today, so what I'm showing you in this slide is a fantasy of the potential future language feature. And it goes like this. For sure, the one thing we can do is to give it a name to this function. Maybe we cannot provide the body, but we can provide a name. It's null terminated. And then it will be executed sooner or later. When it is a predicate, it will be executed. So we have to return something. Because we cannot ever determine the condition, we don't want to give false positives. We will return true. True means I'm not 100% convinced that there was a bug. So I just return true in order not to abort the program too soon. But for the purpose of static analysis, we have this attribute. It doesn't exist today, but it could in the future. And it means to the static analyzer, don't look at the function body. It's just rubbish. Yeah, just focus on the name of the function, treat it as a symbol rather than a definition of the function. And what it buys us, first, we can use it as an expression, because now it's a normal function with a signature, so we can use it wherever you can put a function. So we can express our precondition. And the way it would work, hypothetically, if we get just a row pointer, we have no reason to assume that it is correct during the static analysis, so we report a warning that there may be a contract violation here. But if our function getName has the postcondition now that it will return this is null terminated. Postcondition is a guarantee on the return value. Return value in function signature doesn't have a name, so we have to artificially introduce this R, and then we say that this R is null terminated. If the static analyzer can see this, it can see that the postcondition from this function is exactly the same symbol as we see in the precondition of the other function, so those symbols match, and the warning from the static analyzer is silenced. And this way we have introduced a postcondition to our talk. And this is the primary goal of the postcondition, at least as I see it, is for it to be matched against other subsequent functions' preconditions, and some conclusions from it to be drawn. So let's see the postcondition a bit. Now we have a function that takes two pointers to offers and return better of the two. We have a precondition that we know they cannot be null, and we have a postcondition that the return value R is also not null. And the postcondition, again, is a conditional guarantee. Like, we don't guarantee that it will be true, the postcondition, if our function throws an exception. It's quite obvious, actually, because if there is an exception, there is no returned value, so you cannot even observe it. But we could put it in even stronger words, or invert this property. The primary, if not the only purpose of throwing an exception is to say that we were not able to satisfy the postcondition that we advertised. And the second case where our postcondition will not be respected is when the preconditions are not respected. You can imagine how this function is implemented. I get 2 pointers, and I will just return one of them. So if one of them is null pointer, you will likely get this null pointer back, and I will still be able to say that I satisfy the postcondition. I'm compliant with the postcondition because the precondition was violated. Okay, so for now, what we've seen was comments in the code, or yeah, and this is mostly the comments, because there is no way, even though the contract, the fact how we interpret the input parameters and what we definitely expect of them or don't or not expect of them cannot be communicated in function declarations. So whatever we do is not really satisfactory. The best thing we could do, and some people do it already, is to have a macro like precondition that stores these conditions inside function body. And then it does different things with them depending on how we want to configure the macro. So there's some hash if-defs or whatever, and in one build it just checks and aborts this. In other builds it checks and throws an exception, it does nothing, logs, there's many options, and they are of course useful. They can help prevent damage to the code if the program is terminated early. They can help in testing to detect bugs. But it all feels wrong because they all allow the bugs to happen. We only have to allow the bug, and then we can do something with it at runtime. What they don't do is they don't really prevent bugs from entering the system in the first place. And this is where contracts in the language could help. There were 2 attempts to add contracts to C++ so far, one for C++ 11, the other for C++ 20. They both failed, but we are working on a third incarnation. And the syntax I'm showing you was from the second attempt. We don't know if they will look the same in the third attempt, but maybe. So this looks somewhat similar to attributes, but they are not attributes because attributes would not allow this colon there. But the idea should be clear. Pre means a precondition, this post means a postcondition. And if it worked, we have the ability to declare those preconditions and postconditions as part of function signature. It's better than comment because it is something that the compiler can see and can type system check. So it can see whether A, B, R are, well, not R, but A and B are in scope, whether the expressions make sense. So they are always compiled and in sync. And the good part is that the compiler or the static analyzer doesn't have to look inside the function body to get the relevant information it wants, because it's all there in the function declaration. We made the assumptions in the previous slide that the function should be inline. Now it's no longer there, because only the declaration has enough information for the static analyzer to proceed. In the case with is in range that we had before, there is no need to inject some code or undefined behavior inside, because the predicates, those contract predicates extract all the good parts from undefined behavior, but leave the bad parts alone. So the information for the static analyzer is plain here in the text, but there is no UB anymore. And well, I forgot what I wanted to say. Well, this is there. And even one of the other uses of those annotations is that the compiler can inject some code based on them. So now you can just configure the compiler to put those defensive ifs inside the body only from those preconditions. And even if they are there, this doesn't compromise the static analysis, because the static analyzer gets his message that in form of this predicate. So you can have the best of both worlds. And you can put them in the place where you normally cannot put any code. Like an invariant could be expressed as a declaration inside the class. And you cannot do this even with C asserts, because no declaration, no expression or statement belongs there. And we get one uniform syntax, because static analyzers that are able to detect preconditions are already in the market. But each of them uses their own syntax for expressing those preconditions. And if I'm writing a library, I don't know which tool I should target with my annotations. But if there is one uniform standardized notation for this, it will be obvious. All tools will have to adapt to it, and I will know how to write my contract annotation. And there is one important other thing that we have to talk about, that static analyzers or UB sanitizers can only detect symptoms of bugs, but not the bugs themselves. Like, if I have this function from one of the previous slides, there is quite complicated, and the static analyzer says that something is wrong. But it doesn't know what. It doesn't understand our intentions or what this function is doing. But it understands one thing. We never want undefined behavior in the program. And now if we have preconditions, we never want preconditions to be violated. It can be sure there will be no false positive. It's always, if we can find a path that this is violated, it's for sure not the programmer's intention. We know that this is not the programmer's intention, but we still don't know what the intention is. So if we get this warning, if your goal is to have no static analyzer warnings, the thing you could do would be to just put a defensive if and just skip this call to offer if y happens to be null. Because this is what the static analyzer warning would be, that y can be passed a null pointer. Y can be a null pointer when this function is involved. So if you see a warning and you want to be quickly be done with it, you can just silence the warning. But this way, you are only curing the symptoms, but not the cause of the problem. If your goal is not to see the warnings, you can just skip static analysis altogether. But if you want to fix real bugs in the program, you will have to look at all the code before to trace for the real source of the problem. And the real bug here is this premature try and catch. Apparently, we are assuming that compute offer always returns some proper offer, never a null pointer. And apparently, the idea here was that we first compute the offers, and once we have computed them, we tell which one was better. So if we cannot compute the offer, for sure we don't want to give the answers whether one is better than the other. So the proper way to address this problem is not to put those catch. Usually, putting try and catch is an indication of a bug. It's hardly anywhere in the program that you need to catch exceptions and swallow them. And once we do this, we can see that this defensive if will never be triggered. So we can simplify it a bit. And now, because we have no artificial scope introduced by the try, we can combine the declaration of the object with assigning the initial value. And now not only did we fix the bug, but also the program is program flow and logic is simpler, and we have learned something about this part of the program. And that's basically it. Just to summarize, the most important points is that contracts, and especially the preconditions and invariants, that are expressions of the contract, help detect bugs in a formal way that is understood easily by other programmers, code reviewers, and all the tools there are. There are C++ predicates that can potentially be executed, and if there were to be executed and return false, it means we are sure there is a bug before this condition, or in the condition itself, because condition in a contract is also a piece of code which can contain bugs, but never after. And they can appear in the places like class definitions, which is also a novelty. And with this information can be exploited by many tools, like by static analysis tools, by sanitizers. In the code reviews, they can be used for code generation and even more. But this is a different story to be told another time. Thanks for listening. And
thank you.
If we have some time for questions.
Thanks very much indeed. And we've got just a few minutes for some questions. So if you do have a question, please join us here down the stairs, please. Any questions for Andrzej?
There is one, at least.
There is one.
Coming down.
Or even more than one. Here you are, sir.
Yeah, so your pre and post conditions, especially the symbolic function that you implemented to blindly return true, just for the sake of it, to return something. So this kind of reminds me of using type system and type trait. So you could make a type trait in conjunction with C string that would say or implement the post condition to be always true. Have you thought of implementing post conditions and preconditions using type system?
We actually seen this passing this C string class rather than pointers is a way of doing this. It's like engaging type system.
I mean specifically the function which said is null terminated and always set true. So it would be something like is trivially copyable or something like that. So this is what it reminds me of. And similar things are already present in the standard. So how do they differ? That would be the question.
Okay, so the question is, if I understand it, whether the type traits or similar static mechanisms can be used to detect this kind of preconditions. I'm trying to find the slide, so maybe it will be easier to see. The answer is we cannot, because whether the precondition is satisfied or not is a dynamic property of an object rather than type. Type traits constrain the types, whereas here we are constraining the values of the objects, which we don't know in advance. So statically, we cannot say that this value of the object is okay or not. For some minor subset, we could do it if this is const or compile time expressions. There we could use static asserts to detect those bugs. But then we are still left with those situations at runtime, which there is no other way that we know of to handle.
You mentioned that there were 2 attempts to have postcondition and precondition standardized, but they failed. Do you happen to know why the committee didn't agree to have those mechanisms in the language? What were the reasoning to reject those pre and post conditions from the standards?
I think the reason was the same as with other features that usually don't get into the standard, that it was too new, too unstable. There was no implementation available in any compiler that would prove that it works and that we understand it. So because the question is why the previous standardization effort failed. We only think it works. we know that we need it. We only think that the syntax we invented works, but we are not sure. There was not much investigation being done, experimental implementations, and the corner cases explored. So it was too soon. It was felt that it was too soon to rush it into the standard.
Okay, thank you.
Yeah, Andrzej. So what do you think about optimization based on the preconditions? So like imagine you have a function that cannot work with null pointer, but is using somewhere deep inside function that is checking if it's a null pointer or not. So what is it? Is it something that your proposer is supporting or not?
So the question is
to do optimization based on the preconditions. So for example, you can remove some of the comparison of null pointer when you know that the function has this precondition.
Okay, I'm looking for a slide. So the question is whether those contract annotations, if there are, can be used for performing additional optimizations in a compiler. They could. People, the answer is they could. People are afraid of those we can call it, after the morning talk, the evil compiler optimizations, because the effects are not sometimes surprising. But we could. We can do it even today. Like, we've seen this. We check the condition and react somehow. If the reaction is just to plant undefined behavior, maybe a clever compiler can exploit it. Of course, some people, there are different industries involved here. So when life-critical systems people see this idea that there will be more UB in different places, they are just absolutely scared off. But yes, the other people, if we are talking about the video games, for instance, it crashes, who cares? But if it's faster, if it's twice faster, this is a benefit. This is a real benefit. So they give you this potential. And because it's in the function declarations, you can have even more of this.
Okay, and the last question, please.
Hello, thanks for the talk. So one question for the example on the slide now. The code that is injected for if not A, not B in this example proper. For example, if this function is passed to the sort algorithm, this function would be called multiple times with the same input. So would there be any optimization techniques that it is not checked multiple times, or times for each value?
So there is a concern, this is how I understand your question, that if there is too much of those checks, it may slow the program down. And is the compiler clever enough to do the optimizations? The way we standardize it, the one we want to standardize it, and the way it works today, it is that it is hidden under a macro. And this is in order to give you the control. We don't know what the compiler will do or how clever it is. So you always have the option to switch it off entirely. So this way you get the guarantee that you will not spend a single instruction doing all those runtime checks. There is a switch to turn them all on, and then maybe it's too slow. Whether it can be optimized, I think there is no clear answer to it. I think it depends on how clever your compiler is.
Okay, thank you. And the other one, if we bind a post condition to a value, would that mean that it has to propagate through move operations, assignment operations, and like that? So we have to, when writing those assignments and constructors, to not violate the post condition that has been bound to a value. So
the question is, should I, especially if they are generated by the compiler, should I annotate all those preconditions?
So we bind a post condition to a value, if I got it right, not to a type. And if that value propagates through a program, it is called multiple times, let's say copy construction, move construction, assignments. So what if one of these violates the post condition we have put on it?
I don't think that I understand the question. Like, if you have a copy constructor of a type that has an invariant, because I think this is interesting.
No, not the type, but the value.
So the value is returned from a function.
Yeah.
And the function says there's something about this returned value.
It binds some postcondition.
Yeah, and you know that this is guaranteed only for a tiny fraction of a second, only the moment the function returns and not after. And now I fail to see what the question is.
Yeah, if that tiny second, the answer is that it's there for only a tiny second. I wanted to ask whether it propagates through a bigger part of the program.
No, and you can only assume it the moment the function ends and not after next operations are involved.
Andrzej Krzemieński.
Thank you.